Arrow Lake is Intel's revolutionary new processor for mainstream desktop, featuring new P-cores and E-cores, disaggregated tile-based 3D Foveros packaging, an integrated NPU for AI acceleration, a next-generation uncore, DLVR power rails, and so much more.
In this video series, I have a closer look at Arrow Lake performance tuning and overclocking opportunities. I have a look at the compute, the memory subsystem, and the data fabric. In this video, we have a closer look at the Arrow Lake E-cores.
The Arrow Lake E-cores are located on the compute tile. It shares the tile with the P-cores, the ring, and the caches. An E-core cluster consists of 4 E-cores. An Arrow Lake S processor can have a maximum of 4 E-core clusters, yielding a total of 16 E-cores, like on the Core Ultra 9 285K. The E-cores feature the SkyMont microarchitecture.
The clocking of the Arrow Lake E-cores is very similar to how it was on previous generation Intel processors. We have a reference clock, which gets multiplied by a CPU ratio.
The 100 MHz reference clock frequency is generated internally by the CPU PLL. This clock affects all the IP blocks in the compute tile, including the P-cores, the E-cores, and the ring. This PLL can be linked to the SoC PLL when you run in synchronous mode, or work independently if you run it in asynchronous mode. You can configure the CPU BCLK frequency between 40 and 1000 MHz. In the ASUS ROG BIOS, you can configure the CPU BCLK frequency in the AI Tweaker menu by first setting AI Overclock Tuner to anything else than auto. Then, you can also switch between asynchronous and synchronous mode by adjusting the BCLK mode option.
The reference clock gets multiplied by an E-core cluster ratio. Every E-core cluster consists of 4 E-cores, but each E-core cluster can be clocked individually.
The effective E-core CPU ratio is determined by 3 key inputs: the turbo ratio limit, the per-core ratio limit, and the core minimum ratio.
Let's have a look at these technologies. Generally speaking, there are 2 ways to set the E-core cluster ratio: sync all cores or by using the turbo ratio limits.
Sync all cores will set a single fixed ratio applied to all the cores. This is the historical method of getting a static overclock. Turbo ratio limit configuration allows us to modify the default Intel frequency specification and configure a dynamic overclock. On the Core Ultra 9 285K, the E-core turbo ratio limit starts from 32x, which is the same as the advertised E-core base clock frequency. By default, the E-cores of the Core Ultra 9 285K can clock up to 4.6 GHz, whether a single or all 16 E-cores are active. For the E-cores, we can configure 8 different scenarios. Each scenario has a number of active E-cores and a target ratio. There is a fixed logic, ensuring the scenarios don't overlap. So the number of active cores of scenario n must be higher than the active cores for scenario n plus 1. Furthermore, the target ratio for scenario n must be lower than the target ratio for scenario n plus 1. For example, we can create a scenario where 1 E-core boosts to 5 GHz, up to 5 E-cores boost to 4.8 GHz, up to 13 E-cores boost to 4.7 GHz, and up to 16 E-cores boost to 4.6 GHz. The E-core turbo ratio limit configuration works independent from the P-core configuration. So even if all P-cores are active, if only 1 E-core is active, it will set the frequency to 5 GHz.
Per-core ratio limit allows you to set the ratio of each core individually. It is based on the Intel Turbo Boost Max 3.0 technology introduced in 2016. It's important to note that the per-core ratio limit and the turbo ratio limit act individually. So even if the turbo ratio limit would allow for a higher boost frequency, it won't boost there if your per-core ratio limit prevents it.
The per-core ratio limit plays an important role in the Arrow Lake overclocking process. It's not only the ratio used in the VF point configuration, but also the ratio referenced by many other ratio tuning technologies. The maximum per-core ratio limit is 85x or 120x depending on whether core ratio extension is enabled. In the ASUS ROG BIOS, you can configure the E-core per-core ratio limit via the AI Tweaker specific efficient core submenu.
The core minimum ratio is a brand new feature for Arrow Lake. It allows you to set a floor ratio for the P cores and the E cores. Do note that this ratio is still defined within the P states, so it's not really an alternative for disabling C states if you want to prevent core parking or cores going to sleep.
In the ASUS ROG BIOS, you can configure the minimum turbo ratio via the AI Tweaker Tweaker's Paradise submenu.
Granular ratios is also a brand new feature for Arrow Lake. Basically, the granular ratios allow us to set a CPU frequency in steps of 16.67 and 33.33 MHz. It does this by downbinning from the per-core ratio limit. And that also means that we cannot set a granular ratio as the turbo ratio limit. It really gets downbin from the per-core ratio limit.
For example, if you set a granular ratio of 50.16x, in that case, the per-core ratio limit is set at 51x and then downbinned by 5 steps of 16.67 MHz, which is 100 MHz divided by 6. That is important to keep in mind in case you're also running other ratio configuration technologies. In theory, you can set up to 255 downbin steps from the per-core ratio limit. That can lead to some errors in software reading. Let's say, for example, you set the per-core ratio limit to 50x and then downbin 200 steps of 16.67 MHz. Then the operating frequency would be 1667 MHz instead of 5000 MHz. Fortunately, you'll find that most BIOSes give you a simple interface to set granular ratios. In the ASUS ROG BIOS, you can configure the E-core granular ratio via the AI Tweaker specific efficient core submenu.
Overclocking thermal velocity boost, or OCTVB, is not a new feature for Arrow Lake, but it is new for the E-cores. Basically, this technology allows us to restrict the CPU ratios depending on the operating frequency.
To be more precise, OCTVB is available for the E-cores in per CCP module mode. That means it's available as a configuration tool that downbins from the per-core ratio limit rather than from the turbo ratio limit configuration. As a consequence, the configuration is done per E-core cluster. Each E-core cluster has 2 available OCTVB points, each of which is defined by a target temperature and a number of downbins. Note that the downbins are cumulative, and thus the downbins from point B stack on top of the downbins from point A. For example, let's say we've set the E-core cluster 0 per-core ratio limit to 50x. Then we set the OCTVB point A to minus 2x at 50C and OCTVB point B to minus 2 at 80C. In that case, the frequency will be 5 GHz below 50 degrees Celsius, 4.8 GHz between 50 and 80 degrees Celsius, and 4.6 GHz above 80 degrees Celsius. The OCTVB trigger point is the core-specific temperature. So even if all other cores exceed the E-core cluster's OCTVB temperature point, as long as the E-core cluster temperature does not exceed that temperature, it will not downbin. One last important thing to mention is that, for now at least, the temperature point is 5 degrees off. By that, I mean that if you set the OCTVB point to 55 degrees Celsius, it actually kicks in at 60 degrees Celsius. In the ASUS ROG BIOS, you can configure the overclocking thermal velocity boost per CCP module via the AI Tweaker thermal velocity boost submenu by first enabling overclocking TVB and then setting OCTVB configuration limit to per CCD module.
The voltage regulation for the Arrow Lake E-cores is a lot more complex than on previous generation Intel processors. Basically, that's because of the DLVRs. The DLVRs allow for much lower voltage of the E-cores, but they still rely on an external dynamic motherboard voltage regulator as the voltage source.
Each E-core cluster has its own VF curve, which is defined by up to 7 VF points. The first 6 VF points are factory fused, and the last point is mapped to the OC ratio. Here's the E-core VF curve for my specific Core Ultra 9 285K. The voltage is about 650 mV at 800 MHz, then increases to 1.07 volt for VF.6 at 4.6 GHz. 4.6 GHz is the default maximum frequency for the E-cores. In the ASUS ROG BIOS, you can find an approximation of the E-core's VF points, and thus make the VF curve, in the AI Tweaker Efficiency Core VF Point Offset submenu. Advanced Voltage Offset, more commonly known as VF points, is available for each of the E-core clusters. There are 7 available VF points, 6 of which are fixed to a specific ratio. The final VF point is mapped to the OC ratio, which is the E-core cluster per core ratio limit. If you use granular ratios, keep in mind that those are downbinned from the next full ratio. In other words, the OC ratio cannot be a granular ratio. You can set a negative or positive voltage offset for each of these VF points and for each of the E-core clusters. The final OC ratio's base voltage will be the user-configured adaptive voltage. In the ASUS ROG BIOS, you can configure the E-core VF points via the AI Tweaker Efficient Core VF Point Offset submenu.
To safeguard the processor, Intel has imposed strict voltage limits for the E-cores. Basically, these voltage limits prevent the E-cores from requesting higher voltages to the CPU power control unit.
By default, the voltage limit for the E-cores is 1.278 volt, but this can be increased to 1.37 volt under ambient conditions. When the temperature is below 10 degrees Celsius, you can further increase the voltage limit or disable the limit altogether. If you try setting the limit above the approved limit, the PCU will automatically adjust it to the highest allowed limit. And if you disable voltage limits and the temperature is above 10 degrees Celsius, the CPU will operate in safe mode and limit the frequency to 400 MHz.
For DLVR powered IP blocks, like the E-cores, you can also switch to PG mode and basically work around the voltage limitations because you take direct control over the voltage rail. We'll cover that a little bit later in this video. Thermal velocity boost voltage optimizations is an Intel technology that takes advantage of the fact that CPUs need less voltage to run at a certain frequency when the operating temperature is lower. So as your CPU decreases in temperature, it will also reduce the operating voltage for a given frequency. When you're trying to manually tune the voltage of your Arrow Lake CPU, it's prudent to disable this technology.
When the voltage optimizations are enabled, we can use hardware info to track the CPU VID request as the CPU heats up. I've collected the data for the Core Ultra 9 285K to illustrate this behavior. As you can see from the data, with the E-cores at 4.6 GHz, the operating voltage is 1.048 volt when the temperature is below 50 degrees Celsius. However, it increases to 1.068 volt when the temperature approaches 100 degrees Celsius. A regression analysis tells us the operating voltage changes 0.4 millivolt for every change in degrees Celsius. In the ASUS ROG BIOS, you can enable or disable the thermal velocity boost voltage optimizations via the AI Tweaker Thermal Velocity Boost submenu. The external VCCIA motherboard voltage regulator, or NVVR, provides the input voltage for the individual P-core, E-core clusters, ring, last level cache, and E-core L2 cache. Each P-core, E-core cluster and ring have an individual digital linear voltage regulator, or DLVR, which sits between the VCCIA voltage rail and the IP blocks. That means each of the blocks can operate at its own voltage. VCC Atom is the DLVR powering an individual E-core cluster, which consists of 4 E-cores and its L2 cache. The DLVRs can also be bypassed. In that case, the IP blocks are running in so-called power gate mode or PG mode. In PG mode, the VCC-IA voltage rail directly powers the IP blocks, and they all share the same voltage. That's similar to how previous generation desktop architectures worked.
The default mode of operation is DLVR mode. Let's explore that first.
Based on its VF curve, the E-core clusters request an operating voltage using the SVIT protocol from the CPU Power Control Unit or PCU. The PCU in turn configures the VCC-IA voltage rail and the individual VCC Atom DLVRs. There's 2 ways to configure the E-core voltage: adaptive mode and override mode. Adaptive mode is the standard mode of operation, which relies on the factory-fused voltage frequency curves, which we discussed before. In override mode, we specify a single static voltage across all ratios. It is mainly used for extreme overclocking, where stability at high frequencies is the only consideration.
We can configure override and adaptive mode directly in the PCU by defining a target voltage and a voltage offset for each of the 2 modes.
In adaptive mode, the target voltage is mapped to the E-core cluster's OC ratio. Each E-core cluster has its own OC ratio, which is defined by its per-core ratio limit. This also matches the E-core cluster VF.7. You can configure the adaptive voltage and the OC ratio to any value. However, multiple rules enforce what ratio and voltage is actually set. Rule number 1. The voltage set for a given VF point n must be higher than or equal to the voltage set for VF point n-1. In the case of the E-cores, that means that the voltage for the OC ratio must be higher than or equal to the voltage for VF.6. This can be a little bit strange because you can program the OC ratio to any value, including lower than 46x. For example, let's say you've set the E-core per core ratio limit to 40x and the adaptive voltage to 1 volt. In that case, VF.7 will be programmed to 40x at 1 volt. However, the actual frequency will be 4 GHz with 1.078 volt, as that's the voltage for VF.6. Rule number 2. For ratios between the OC ratio and the next highest factory-fused VF point, the voltage is interpolated between the set adaptive voltage and the factory-fused voltage. Let's say we configure the E-core VF OC point to 50x and 1.25 volt. The target voltage for E-core ratios between 46x and 50x is now interpolated between the factory-fused voltage for 46x and the set adaptive voltage for 50x. In the ASUS ROG BIOS, you can configure the E-core DLVR voltage in the AI Tweaker menu. You can configure in adaptive, manual, and offset mode.
2 additional notes about using adaptive voltage mode.
First, the adaptive offset is applied across the curve. So if we set a plus 100 mV adaptive offset, the operating voltage for all frequencies between 8x and the OC ratio will be increased by 100 mV. Second, any adjustments made to the VF curve is still subject to the aforementioned rules for adaptive voltage. That includes the adjustments for the VF points. For example, let's say the E-core cluster 0 voltages for VF points 5 and 6 are 0.9 volt and 1.05 volt respectively. If I configure a minus 200 mV offset for VF.6, then the effective voltage will be 0.9 volt, not 0.85 volt, because adaptive voltage rule number 1 is enforced.
Intel per core voltage is an Intel technology that allows you to specify a voltage for each E-core cluster individually. Do note that this only works when DLVR mode is enabled.
Just like in DLVR mode, you can configure the per core voltage in adaptive mode and override mode, specifying a voltage for the defined per core ratio limit or across the VF curve respectively. The per core voltage implementation for Arrow Lake is slightly different than prior platforms, as each E-core cluster now has its own OC ratio. Functionally, each E-core cluster's per-core voltage is mapped to its per-core ratio limit and thus also serves as the base voltage for VF.7. The standard rules for adaptive voltage mode still apply for each E-core cluster. As a consequence, it means that each E-core cluster's VF curve is truly independent, as voltage interpolation is done for each E-core cluster separately. Let's say we configure the E-core cluster 1 VF point to 50x and 1.25 volt, and we set the E-core cluster 2 VF OC point to 52x and 1.3 volt. The target voltage for E-core cluster 1 ratios between 46 and 50x is now interpolated between the factory fused E-core cluster 1 voltage for 46x and 1.25 volt for 50x. For E-core cluster 2, the ratios between 46x and 52x are interpolated between the factory fused E-core cluster 2 voltage for 46x and 1.3 volt for 52x. In the ASUS ROG BIOS, you can configure the per E-core DLVR voltage in the AI Tweaker specific efficient core submenu. You can configure it in adaptive, manual, and offset mode. In power gate mode, all the DLVRs tied to the VCC-IA voltage rail are bypassed, and the connected IP blocks are powered directly by the VCC-IA voltage rail.
Power gate mode is basically how the VCC-IA voltage rail worked on the previous generation, Raptor Lake. For Arrow Lake, it also works, but it's a little bit complicated.
To make a long story short, when the P-cores, E-cores, and ring request their voltage to the CPU PCU, they account for a ton of other compensations, including voltage droop, DLVR efficiency, AVX guard bands, thermal velocity boost voltage optimizations, and so on. The result is that the actual voltage provided from the VCC-IA voltage rail to the DLVRs is relatively high. For example, here are the voltages with a CPU at stock voltage and frequency running a light all-core workload. We can interpret this as follows. The P-core, E-core, and ring request a voltage to the PCU to ensure it's running 1.15, 1.05, and 1.1 volt respectively. The PCU then adds compensation for the load lines, CEP, TVB, AVX, ACLL, DLVR efficiency losses, and so on. At the very end of the calculation, the PCU determines that the VCC-IA voltage rail should provide 1.43 volt input voltage to the DLVRs. If we were to switch to power gate mode, but maintain the same mechanism for calculating the required voltage, then the VCC-IA voltage rail would effectively provide 1.43 volt to the P-cores, E-cores, and ring. That's obviously way too high for the target frequency and would quickly result in an overheating system. But this is how the voltage was configured on previous generation Raptor Lake processors.
Fortunately, there's another way to approach power gate mode. Ignore all the SVID requests and calculations and set the VCC-IA voltage regulator directly over PM bus. That basically means that we have direct control over the VCC-IA voltage output.
This approach is a very traditional way of overclocking, whereby you set a fixed output voltage and then use an appropriate VRM load line setting to reduce the operating voltage in higher load scenarios. Let's have a look at an example and compare power gate and DLVR in Cinebench R23. If we set 1.35 volt with LLC6, then the effective voltage under load is 1.26 volt. That's about 150 millivolt higher than with DLVR. Despite the much higher voltage though, the temperature is only 7 degrees Celsius higher than what we got when we were running with DLVR. If we set 1.3 volt with load line 4, then the effective voltage under load is 1.15 volt, which is very similar to DLVR. Despite the almost identical voltage for the P-core, E-core, and ring, the operating temperature is 7 degrees Celsius lower than what we got with DLVR.
The bottom line on DLVR versus power gate mode is that it appears that DLVR will give us better temperatures and power consumption in low load scenarios, whereas power gate mode seems to give us better temperatures and power consumption in higher load scenarios. And that's because of the power loss associated with a linear voltage regulator. Basically, the power loss translates into heat, and the heat eats into our thermal budget. And because we have less thermal budget, we have less overclocking headroom with DLVR. How much less, and what is the power loss?
Well, the power loss across a linear voltage regulator equals the decrease in voltage across the DLVR multiplied by the total load. In our example, with a drop of 305 mV and a 160 amps load, the power loss is almost 50 watts. Nearly all of that power loss will convert into heat.
For higher load scenarios, it seems that power gate mode provides us better overclocking headroom because the operating temperatures are lower. But we cannot rely on the voltage calculations of the PCU because they're too conservative, and therefore the voltages will be too high. So if you're going to use power gate mode, then it's better to ignore all of the SVID calculations and set the VCCIA voltage rail directly. Do note that you also need to set an appropriate VRM load line to make sure that the voltage is low enough in high load workloads.
In the ASUS ROG BIOS, you can switch between DLVR and power gate mode for the VCCIA voltage rail in the AI Tweaker menu by configuring the CPU DLVR mode menu item. In the ASUS ROG BIOS, you can set the VCCIA voltage rail in the AI Tweaker menu by configuring the actual VRM core input voltage in manual mode.
The E-core power consumption is primarily governed by the Turbo Boost 2.0 technology. Intel Turbo Boost 2.0 allows the processor cores to run faster than the base specification if it is within the thermal, current, and power limitations.
The Turbo Boost algorithm works according to an EWMA formula. This stands for exponentially weighted moving average. There are three main parameters to consider: PL1, PL2, and tau. Turbo Boost 2.0 technology has evolved over the past couple of years to incorporate many power, thermal, and electrical performance limiters. To cover each in this video would take up way too much time. Fortunately, Intel provides two performance profiles for the Arrow Lake SKUs, which configure all these settings for you. For the Core Ultra 9 285K, the Turbo Boost 2.0 profiles are Performance and Extreme.
Should you wish to override the Intel performance profiles, you can do so in two ways. Either directly override the Turbo Boost 2.0 parameters in the BIOS or enable ASUS MCE. ASUS Multicore Enhancement is an ASUS technology that enables higher performance out of the box by tuning some of the Turbo Boost 2.0 parameters.
Note that you can select an Intel performance profile and enable MCE at the same time. The effect will be that MCE overrides the most common Turbo Boost 2.0 parameters, such as the PL1 and the PL2, but will adhere to other limiters, such as the current excursion protection configured by the Intel Performance preset. The ASUS Advanced OC profile is a more elaborate, unleashed overclocking profile than multi-core enhancement, as it doesn't just adjust the major Turbo Boost 2.0 parameters, but also implements a lot of BIOS auto rules to facilitate overclocking.
Overclocking the Arrow Lake E-cores is very similar to how it was on previous generation Intel processors, with one main exception. The Arrow Lake E-cores have pretty good IPC and clock pretty well. So unlike previous Intel processors, we love the E-cores, and it's a good idea to prioritize E-core tuning over P-core tuning.
Let's compare the performance improvement in Cinebench R23, changing the P-cores and the E-core clock from 4.6 to 5 GHz. The performance improvement from overclocking the 4 E-core clusters is about twice that from overclocking the 8 P-cores. The E-core overclocking range is also quite good. With 1.25 volt, I could increase the E-core frequency to 5.1 GHz in Cinebench R23 with a 360 AIO. That's a 500 MHz increase from the base frequency of 4.6 GHz. The cores can reasonably undervolt as well. I could achieve a minus 75 mV undervolt at 4.6 GHz, effectively reducing the operating voltage from 1.078 volt to 1 volt. At the lower end of the VF curve, I could even undervolt the cores to below 0.5 volt at 400 MHz.